Welcome back to the deep dive. Today, we're looking at matter. I mean, it's literally everything, but maybe not in the ways you usually think.
Exactly. We know the basics, sure.
Yeah, like what fundamentally is air or water or even, I don't know, a stone you pick up?
Uh-huh.
We're aiming to get past just the definitions today.
Right. It's about the unseen action, the constant buzz that makes reality,
Mm.
well, real.
Okay, let's unpack this.
So the core idea is simple enough, right? Matter is just anything that occupies space and has mass.
Okay.
Think air, water, sugar, stone, the stuff our world is made of. These are the fundamental building blocks.
Simple definition, but then it gets complicated. Because matter isn't always the same. It doesn't behave consistently.
Precisely.
Yeah.
And that leads us straight to the three main physical states we generally talk about. Solid, liquid, and gas.
Right, the big three.
Yeah. And each one's got its own personality, you could say, based
Okay.
on how its tiny particles are acting.
So solids first?
Solids, like ice or that stone again. They have a fixed shape, a fixed volume. The particles are packed super tight, vibrating, but stuck in place.
So you can't really squash them?
Nope, not easily, anyway.
Yeah.
Then you got liquids, water, oil, you name it.
Okay.
No fixed shape. They take the shape of the container, right?
Right.
But they do have a fixed volume.
Uh-huh.
And they can flow because the particles can slide around each other.
Yeah.
Still close, but looser than solids.
Make sense? And gases.
Gases are the wild ones. Think air or oxygen, no fixed shape or volume.
They just go everywhere.
Pretty much. Particles are miles apart, relatively speaking, moving like crazy, totally independent. That's why you can compress gas so easily and it'll fill up any space you give it.
Okay, but here's where it gets really interesting. You said particles. We need to zoom in, like way in.
Yes, because the properties of these states come from what the particles themselves are doing.
And what are they doing? What are these particles like?
Well, first, they are incredibly small, like
Right.
mind-bogglingly tiny. Second, there aren't actually spaces between them, even in a solid.
Really? Even in something solid, like a rock?
Yep, tiny spaces, but they're there. Third, and this is crucial, they are always moving, constantly in motion.
Always. Even in ice.
Even in ice, they're vibrating like mad. And fourth, they attract each other. There were forces pulling them together.
Hang on. If they're always moving, and there are spaces, and they're attracted, how does anything stay solid? How do they stick together? It feels a bit contradictory.
It does seem that way, doesn't it? It's all about a balance, really. A tug of war between the particles' kinetic energy, that's their movement energy, and those attractive forces pulling them close. In solids, the attraction wins, mostly. It locks them into place, even while they vibrate. But add energy, like heat.
Then the movement energy increases.
Exactly. You give those particles more kinetic energy, they start overcoming the attraction, moving more freely. And that's how we get changes of state.
Right, so it's not magic, it's just temperature or pressure changing that balance.
Precise.
Which leads to the transformations we see constantly, like melting solid ice turning to liquid water when it heats up.
Yep.
And freezing is just the reverse, liquid to solid when it cools down.
Correct.
Then evaporation, liquid turning into gas. Boiling water makes steam, that's evaporation.
Heating does that.
And condensation is the gas cooling back down into a liquid, like seeing your breath on a cold day.
Exactly. Water vapor in your breath turns back to tiny liquid droplets.
But there's another one, isn't there? A less common one?
Yes. Good catch. Sublimation. It's quite fascinating, actually.
What happens there?
Sublimation is when a solid turns directly into a gas. It just skips the whole liquid phase entirely.
Wow, skips it completely. Like what?
Think of camphor or dry ice, solid carbon dioxide. It doesn't melt into a petal. It just vanishes into gas. Naphthalene balls, mothballs do it too.
So it just bypasses being a liquid? That's pretty neat.
It is. It
Yeah.
shows how direct that energy input can sometimes be.
Okay, let's circle back to evaporation for a second. It's so common. Like drying clothes. Why do they dry faster some days? Is it just heat?
Heat's a big part of it, yeah. Temperature is key. Hotter day, particles have more energy, they escape as gas faster. Simple as that.
Makes sense.
But it's not the only thing. Surface area matters a lot too.
How so?
Well, if you spread your wet clothes out wide, more surface is exposed to the air, right? More water molecules can evaporate at the same time. Faster drying.
Ah, right. Don't leave it bunched up.
Exactly. Then there's wind speed. A windy day helps whisk away the water vapor that's just left the clothes.
Clearing the way for more to escape.
You got it. It speeds things up. And finally, there's humidity.
Okay, how does that work?
Humidity is how much water vapor is already in the air. If the air is already really damp